AP Chemistry Problem Demonstration Project by Chloe Desus. Hess's Law. Problem. Use the values of the change in enthalpy at standard conditions of the chemical reactions given to calculate the molar heat of formation of aqueous nitrous acid. Those are the equations given. So the first step to solving this problem is finding the equation that we need, the balanced chemical equation, for the formation of aqueous nitrous acid. So in whole number ratios, this is this. So 1 mole of H2 plus 1 mole of N2 plus 2 moles of O2 yields 2 moles of HNO2, which is nitrous acid. However, the molar heat of formation refers to only 1 mole formed of nitrous acid, and so just by dividing the first chemical equation by 2, we derive the equation for the formation of 1 mole of aqueous nitrous acid. So we then need to manipulate the 4 other equations to be able to use Hess's law and calculate the enthalpy change associated with this reaction. So I'm just going to put this in the corner. There we go. And so my first step was looking at this. I knew that I needed to have nitrous acid as a product. So I took the only equation that has nitrous acid in it, which is this one. And in order to have nitrous acid as a product, we need to reverse the reaction. So Hess's law says that when we reverse a reaction, the change in enthalpy changes sign. So if you had an endothermic reaction and you reversed it, it would become exothermic. Seems logical. So this is the new equation. We have NH4NO2 yields NH3 plus HNO2. So we have that nitrous acid now as a product. And as you can see, the enthalpy has changed signs. So that is our first important reaction. The next one I wanted to do was cancel out the NH4NO2. So that's been color-coded because all of the color-coded items will need to cancel out in the final equation. So this is another one of the equations that we were given, one of the originals, that also has NH4NO2. So again, in order to cancel this out, we need to have NH4NO2 both as a reactant and as a product. And for this, we have to, again, reverse the reaction and negate the change in enthalpy, which yields this reaction. So as we can see, the NH4NO2 now is going to cancel out. So next I focused on the ammonia, the NH3, and this is a slightly different process than the two previous equations because this one doesn't need to be reversed. However, for Hess's law to be applied, we need to have the same number of moles on the product side and on the reactant side. In this case, we have 2 moles of ammonia on the reactant side and 1 mole on the product side. So, in order for the ammonia to cancel out, we needed to divide the first equation by 2. So here we have just NH3, not 2 NH3, NH3 yields 1/2 N2 plus 3/2 H2. And the last equation that we have to deal with involves water. So this cancels out our last water. We can see we have the NH4NO2 canceling out, we have the NH3 canceling out, and with the last equation that we have, nothing needs to be changed since the H2 is already canceling out. So these are our 4 equations, and when we cancel everything out and and add together everything that we have left, we ended up with this reaction, this chemical reaction. And as you can see, we have the N2, we have the 2H2, 2O2, O2, and the HNO3, and then the half N2 and the 3/2 H2. So this is simply simplifying the equation and creating it, adding all four previous equations into just one. So this equation, now what we need to do to have it become this equation is to have all of the nitrogen atoms, all of the moles of nitrogen, all of the moles of hydrogen on the same side. The oxygen and the nitrous acid we don't have to do anything about. And so for this, very simple, all we have to do is subtract. Because 1/2 mole of N2, and we have half a mole here, a whole mole here, and obviously this is going to cancel out. So because 1 minus 1/2 is 1/2, so this is how we get the 1/2 N2. And then the same thing happens with the H2, 2 moles of H2. When you subtract 1.5 moles, we also get half a mole of H2. So there we go. This equation becomes the new equation, and we have the original equation that we were aiming for. And so this step doesn't have to do with anything with the enthalpies. So this is unimportant now. And so the next step is to use the equations that we calculated, use the steps that we figured out how to lead up to this point to calculate the enthalpy. So this goes back up in the corner, and I'm going to bring out these equations again. So as we saw, all of these chemical equations, when they are added up, are equal to this one. So our goal equation. And so we Hess's law says that we can add up the enthalpies because the enthalpies of the steps are equal to the enthalpy of the whole step. So we have here we have the steps, and here we have the whole, so to speak. And what do we get when we add all of these up? We get negative 128.85 kilojoules. So before going any further, I always think it's important to look at the answer that we got and think about whether or not this is logical. So we were talking about the formation of aqueous nitrous acid, and the fact that the change in enthalpy is negative means that the overall equation, chemical reaction, is highly exothermic. And this would be logical because the bonds that are being broken are much stronger bonds than the ones that are being formed. The bonds between diatomic molecules have more strength in them and thus release more energy when they're broken. And so the negative value does seem to be logical, and now we can look at significant figures. And so we have this, but we started off with significant figures with only 3 because of the negative, the 37.7. And so we end up with a final answer of 129 kilojoules. So the molar heat of formation of aqueous nitrous acid is negative 129 kilojoules.